Hi students, this is Ms. Skokin. We're continuing on our work in polynomials with section 6.3, polynomial functions. Our objectives are to evaluate polynomial functions, and remember that evaluate means find the value of. Our second objective is to identify general shapes of graphs of polynomial functions. And what that means is we're going to be making connections between what we see written out as the function and what that does to the graph. Pause the video now to read the vocabulary on your own. All right, now that you've turned the video back on, let's take a look at what a polynomial in one variable is. We have an example here, and basically what it is a polynomial that has only one variable in it. Pretty self-explanatory. One of the things that we're interested in is the degree of the polynomial, and it's the highest exponent of the variable that we see amongst all the terms. So if we put the polynomial in descending order by degree, then the one that's on the left is going to be the one that has the highest degree. In the polynomial in our example, the degree is 7 and the leading coefficient is 3. Again, pause the video so that you can read the information in the box. All right, the box tells us that when we have a polynomial of degree n, we write it in descending order as the polynomial in the box is written. And you notice that a sub 0 through a sub n are our coefficients. A sub n is actually our constant term. A sub n minus 1 is our smallest coefficient of the variable x. They are real numbers. A sub 0, or the leading coefficient, cannot be 0, otherwise it's not going to be a leading coefficient. That term would drop out. And n represents, n remember is the highest degree, n represents a non-negative integer. So we're talking specifically about positive integers in our polynomial. I'd like you to pause the video and try this next example. It says find a sub 0 through a sub 7. Those are all of the coefficients of the variable terms, and find n, which is the degree of our polynomial, and then state the leading coefficient of the polynomial. Turn the video back on when you've done that so you can check your answers. Now that you've turned the video back on, make any corrections that you need to make. Notice that I did put some notes in there for you so that you have an idea of what we did when you look back on your notes. If you didn't copy those in, that's okay. Just make sure if you need to, you do copy them in. In the next examples, 1 through 4, we're going to state the degree and leading coefficient of each polynomial in one variable. So we need to make sure first that it's a polynomial in one variable. And if it's not, we need to say why it's not. So pause the video now and try these out. Remember, state the degree and leading coefficient if it's a polynomial, and if it's not, say why it's not. Turn the video back on when you've completed this. Okay, now that you've turned the video back on to check your answers, make sure, even if they're not in order, given to you in order, that you put the terms in order by descending degree so that it's easy when you look at it, the leading coefficient and the degree just jump right out at you. In general, a polynomial function of degree n in one variable x is an expression in the form p of x is equal to, and remember, a sub 0 is the leading coefficient, x to the n power, n is the degree of the polynomial. And then it descends, we increase the subscript of a of our coefficients all the way until we end up to our constant term a sub n. And n, recognize, is the same n as a degree. So you're going to have, if you have a polynomial of degree 4, you're going to have the constant is going to be a sub 4, and you start counting with a sub 0. So you're going to have one more term because you have a constant term that doesn't have a variable. Or if you want to think of it, the variable here is to the 0 power. So the degree of that term is 0. All right, let's take a look at the next page of notes. All right, to evaluate a function, remember, evaluate means find the value of. To evaluate a function, we're going to plug in the value of the independent variable and then determine the value of the dependent variable. So in this case, in example 5, a and b both, what we're going to do in a is plug in 1 each time we see an x. And that's going to be set up. We did this in class, if you remember, and I told you, just to make sure that you don't get confused, it's easier for you if you set it up this way. and then plug in. And then evaluate, do all the math that you need to do, get it in simplest form. So what I'd like you to do now is turn off the video, try example 5A and 5B, and then turn the video back on to check your answers. You should have found 5A and 5B fairly straightforward. We're just plugging in a constant for x in each of these. If you need to make any corrections, stop the video now and make your corrections. Remember to box your answers as you're working so that that really stands out for you. And just a reminder, part B of number 5 had a negative value. So remember, your power rules are going to be consistent with negatives and positive, but they're going to be different between negatives and positives. All right, number 6, A and B, we're going to set up exactly the same way, except this time instead of plugging in a constant value, we're plugging in a variable. Or in the case of 6B, a power of a variable, y cubed. So you're going to set it up exactly the same way. But this time what you're plugging in is a little bit different. So go ahead and set it up, do 6A and 6B, and when you're finished simplifying as much as you can, turn the video back on to check your answers. Once again, I hope you found these relatively straightforward. The only thing that you needed to remember that was a little bit different from the plugging in a constant was that we need to be careful with our power rules and these variables. All right, we're going to try example number 7 and 8 now. And they are going to be a little bit different because if you notice, instead of plugging in a constant or a variable, we're plugging in a binomial this time. The rules are exactly the same. Set it up, plug it in, and then just do the math. You shouldn't find any difficulty with number 7. Number 8 is going to feel a little bit more complicated, but it's really not. So let's do number 7 first. We'll set it up and then do the math. As you can see, the little trick of setting up the parentheses without anything inside of it, kind of according to whatever b of t is defined as, kind of makes it a little bit easier to plug it in and then figure out what you need to do. In this case, we have 2 times 2x minus 1 squared. What this means is we're going to have to FOIL first. After we FOIL, multiply by 2, and then combine like terms with everything else that we've got in the definition of b of 2x minus 1. The left-hand side you're not going to do anything with, okay? It's only the right-hand side. So go ahead and FOIL, simplify as much as you can. When you're ready to check number 7, turn the video back on to check your answers. As you're checking your answer to number 7, I'm just going to put a little reminder down here. If you noticed, I didn't FOIL all the way through because, as I've explained to you before, when I took algebra, I had to memorize the pattern. This is the pattern. If you find it simpler to memorize, then go ahead and do that. If you don't want to do that, it's just going to take you one more line of work to do the FOILing. All right, let's take a look at number 8. This time we have the same b of t, 2t squared plus t minus 1. So that hasn't changed. But this time we've got something that looks a little bit more complicated. We're not just finding b of 2x minus 1. We're finding b of 2x minus 1 minus 3 times b of x. So once again, we're going to set this up. But what I want you to remember is we just found b of 2x minus 1. So we can plug that in directly once we set it up. So if we substitute in what we just found in number 7, b of 2x minus 1, then the only thing we need to do to figure it out is figure out what b of x is. And remember, b of x means we're just substituting in, instead of t, we're substituting in an x. So what's that going to look like? You're right, 2x squared plus x minus 1. Once we put that in, we can combine like terms, simplify, and come up with our resulting polynomial. So what we started out with, b of 2x minus 1 minus 3 times b of x, ends up not being as complicated as it started out looking. We do a simple substitution and then plug in x for t, simplify, combine like terms, and we come up with our answer. All right, we're going to shift gears just a teeny bit now. We're going to start to talk about, on the next page of notes, behavior of functions. Behavior of functions refers to a lot of different things all grouped together, but just like we saw with quadratic functions, if it had a negative leading coefficient, it was downward facing. If it had a positive leading coefficient, it was upward facing. So that's an idea of what we're going to be talking about in terms of behavior. In this case, we're talking about graphs and end behavior of polynomial functions. And graphs of polynomial functions can have real roots, or x-intercepts. The maximum number of real roots a polynomial can have is the same as the degree of the function. The maximum number of x-intercepts that a fifth degree polynomial can have is 5. The minimum number of real roots, or x-intercepts, that a polynomial can have is 1 for a polynomial of odd degree and 0 for a polynomial of even degree. And a polynomial of even degree is something that we're familiar with. If you remember, our quadratics that we did with the parabolas in chapter 5, those are even degree, degree of 2. And so if we have our quadratic, it could be 2, or it could be 1, or it could be 0 x-intercepts. And so that's why a polynomial of even degree could be 0. A polynomial of odd degree, which is going to be like the x cubed, is going to have a different behavior, and we're going to see it's going to have to go through, whether it's positive or negative, it's going to have to go through the x-axis at least once. So it's always going to be a minimum number of one real root. All right, let's take a look at what we see in even degree polynomials. So we're going to graph y equals x squared. That's the parent function. Notice that to the left we have negative values of x, to the right we have positive values of x, and up we have positive values of y, and below we have negative values of y. So when we start to talk about the behavior of this function, what we're going to do is we're going to do it as we read from left to right. So what happens to y as x goes to negative infinity? Well, what that's referring to is, imagine that you're starting at the y-axis and you're working your way to the left. What do we see y doing? Well, we see f of x. Which way is it going? Up or down? Right, it's going up. So it's going to positive infinity. Okay, now what happens to y as x goes to positive infinity, or starts at the y-axis and goes to the right? Well, f of x still is going to positive infinity. And this is the behavior that we see when we have a positive leading coefficient. All right, let's take a look at what happens when we have a negative leading coefficient. Same graph, that quadratic parent function, but this time we have a negative leading coefficient, -1. We're going to graph it as the parabola that goes through the origin. Remember, x goes negative to the left and positive to the right. Y goes positive up and negative as you go down. So this time, as we start at the x-axis and we go towards negative x, or x goes towards negative infinity, what do we see y doing? Well, y is also going to negative infinity. When we start at the y-axis, or the center of the graph, the axis of symmetry, and we go towards the right, or towards positive infinity, what do we see y doing? Well, y, or f of x, is still going towards negative infinity. All right, that's again positive and negative leading coefficients with a function of, or a polynomial of even degree. So let's take a look now at what happens when we have a function of odd degree. With a function or a polynomial of odd degree, in this case y is equal to x cubed, what happens as we go towards the left, or towards negative infinity in the x direction? Well, we see f of x is going towards negative infinity. It's going downward. What about as we go towards the right? Well, in this case, as we go to positive infinity in the x direction, we see the y's also going to positive infinity. What I'd like you to do now is pause the video and predict what's going to happen when we have a negative leading coefficient on that y equals x cubed polynomial. Okay, check your answers, go on to the next page, try those examples 9 times. We're about to run out of time on the video, so once you've done these examples, check your work on the posted notes.